Hi there. In this video, I'll give you an intro onto various OLED displays available in the market, and I'll also show you how to connect them onto the Raspberry Pi Pico board. I bought a couple of 128 by 64 displays. This is basically a 128 pixels widthwise and 64 pixels of height. So they look almost like square, but a little rectangular. You also find long rectangular bar displays, which are like 128 by 32. I didn't buy them, but I bought a couple of displays and with different variations. Well, primarily all of these displays which I have here, which are available commonly in the Indian market, they are based on two possible display controllers. And that is the SSD1306 controller, or it would be an SH1106 controller. So I have both of these combinations in here. Let me just show you all these displays and how the pinouts are. The first two displays that you see on top, these are from Waveshare. They come with 8 pins, which means they actually provide an SPI interface for communication. So if at all you want to configure this display, you need to use the SPI library and configure the GPIO pins as SPI pins to actually work with these two displays. There's also another variation which is actually not from Waveshare, but it's got 7 pins, right? Which also uses the SPI interface. And these three displays, the 8-pin displays that I'm talking about, these are based on the SH1106 display controller, right? There's also another commonly available display that you see here, which has just got 4 pins, right? So you can actually see there are 4 pins if you really check it up in this case. And this display, let me just zoom this a bit. I can just zoom it a little more and just focus on this display alone. I'll show you each of them. So when you look at this display, it's got just 4 pins. This is a very commonly available display too, and this is a 0.96 inch display. I'm not sure whether the 0.96 inch is the diagonal width, because I thought it's got to be the diagonal as such, but when I actually measured up from my scale, it happens to be that the diagonal is not actually 0.96 inches, much larger, but it looks like it's the width of this side. The width of the side seems to be 0.96 inch. I can just show it to you over here. It measures 0.96 inch when you actually checked this particular width as such, right? Let me just unzoom this a bit. I can show you. So you can actually see that it is this width that's shown up as 0.96 inch, and it's not the diagonal. The diagonal is slightly longer. It's also possible that the displayable area is 0.96 inch. Maybe there are some top parts which are like the bezels, which might have some gap. So that could be the reason. And they also have the other variant, which is the 1.3 inch display. So you can see the difference in the sizes. And also note that this display might look very big because it's got more board area. I have another 1.3 inch display, which actually might look a little smaller than this. Not this, I think, sorry, this one. When this one is a 1.3 inch display, so is this. Actually, the display size is the same, just as the board profile of this particular board is much smaller. It doesn't have extra gaps that you find, extra board space that you find on this particular display. And by the way, if you look at this 1.3 inch display, when this actually is not the diagonal, I apparently checked it up. It is the width of this area, because the diagonal measures to be 1.5 inch, roughly around that number. But when you measure this one, this side, it's 1.3 inch. So that's what there seems to be, right? It's about 1.3 inch on this side, roughly around that number. So having said this, these are the two popular sizes of the display. You might also find a 1.5 inch display, which will be a little more larger in screen space than this. And the chipset would most likely be either a SSD1306 or an SH1106 chip. So this display, which I found here, let me just zoom this again a bit. It's got just 4 pins. When you find a 4-pin display, which just have 4 pin outs, the interface would be an I2C interface, or a I2C or I2C interface, right? And you can see that there are 2 pins which are represented for power supply. You'll find the first one is a ground pin. Like you can see here, there's a ground pin. And you can also see a VDD pin. Sometimes it'll be labeled as VCC, sometimes as VDD. The first pin is ground, second pin is VDD. Then you have another pin, which is the SCK pin, which is also sometimes labeled as CLK or SCL in certain displays. They actually mean clock, right? And there's also an SDA pin, which is the data. So these two pins are used for communicating via I2C. That is the SCK and the SDA pin. And these are the ones that you'll actually connect to the appropriate I2C pinouts of your Raspberry Pi Pico if at all you want to program that. I'll show you how that can be done in a while from now. You have the same display. I got another one, which is also the same as this. But there's a small difference here is that okay, let me just move this across and keep this side by side so you can see it better. Yeah. In here, the first pin is ground and the second pin is VDD. However, in this display, you can see that the first pin is actually VCC. It's the same as positive supply. And the second pin is ground. So you have to be a little careful about the pinouts. The pins come in various configurations from what I've seen here. So these are the 4-pin displays which primarily uses I2C. These two displays I've checked up. They actually require an SSD1306 library. That means they are running on SSD1306 display controller. There is also another slightly larger display, which is the 1.3 inch display, which is also 4-pin by the way, which is here. Let me move this across. I can show you. So you can see that this is also a 4-pin display, right? And this has VCC in the beginning, not the ground. It's got VCC, followed by ground, then followed by SCK and SDA. This is a 1.3 inch display, but then this also uses I2C, but the driver for this is not SSD1306 when I checked it up. It's only by trial and error I got to know it. It is actually based on SH1106. If you're buying from online stores, I would recommend you to look up the description. So if I were to buy it from some credible online stores like robo.in or even RoboCraze, they actually provide the complete details about the technical specifications of the display. They might actually indicate whether it's a SH1106 or SSD1306 kind of a display. They're actually documented. So you might want to make a note of that. So if you randomly get the display, you cannot make any assumptions because when you look at the back, there's nothing much being shown up here. You can see this in my Zoom screen. It just shows up 1.3 IIC, there's I2C connection, and it tells you about a couple of these labels for all the resistors and so on. I also saw this number, and this number is nothing to do with the display, I guess. It's got to do with this actual OLED display itself, not the display controller that's sitting behind it. So it looks like it's the OLED display's model is what you see. I can see that as GME 12864-78. But then if you see, this is actually based on the SH1106 driver. That's what works for this. But I have the similar display which is there here. If you see, the top label is almost similar. You can see the top label in here. When this also reads GME 12864, but -42. But this looks like it's the specification of the display the display itself and not the display controller. But anything about the display controller, there's nothing being mentioned in here. So that's one thing. So you can see even here, no mention about what kind of driver you need, whether you need to use SH1106 or SSD1306. Nothing is mentioned in here. So you need to do a little bit of trial and error to check it out. So all of these are I2C displays because they just have 4 pins. Then you have the other kinds of displays, which are, there's one other display which I found, which has actually got 7 pins in here. So when you actually see a 7-pin display, it is in all likelihood, it could be an SPI based display, SPI interface display. You can see they're all labeled nicely. It shows ground, VCC, these both actually for the supply. And this SCK is nothing but the clock pin. You need to connect to the clock pin or SCL pin on your Raspberry Pi Pico if you're going to be using SPI interface. And you'll also see SDA, which is also sometimes labeled as DIN or data in some of the displays, which is the data pin, right? The CL data pin. You also have an RES pin, which stands for reset pin. And there is another pin, which is the DC pin. DC stands for data or command pin, which is meant for sending data or commands. That pin will select, right? Whether the data, the SDA pin is sending data or command is selected by this DC pin. And you'll also find another pin, which is called as a chip select pin or CS pin, which is there here. So you'll find so many pinouts in this. Totally, there are 7 pins, and all the 7 pins needs to be connected to make it work, right? This display backside is no different. Nothing is mentioned other than the fact it's a 1.3-inch OLED display. No information about the display driver that's required for this or what display controller is there in this. And even this label is the same as what you see on the other one, right? So the one that you see here is almost got the similar label. Looks like they all have the same OLED display panel apparently, but then I think that's the number for the display panel, but the actual display controller might vary, right? So though this is actually this 4-pin display, which I'm showing you here, this is SSD1306, but this one is 8-pin display, which is an SH1106, right? So we can see that right here. Finally, you have 2 displays which are more popular. Many people buy this. This comes from Waveshare, which you can see here. This is a Waveshare 1.3-inch OLED display. There is a lot of details about this table. Basically, these are like jumper switches which are there here. So you can see that both of them are not shorted. But when I actually checked up with the continuity tester, they actually is lighting up the LED. So I am not sure. So maybe you need to still short this pins, either this pin to this pin or this pin to this pin, to make up different kind of interfaces, whether you want to use 3-wire SPI or 4-wire SPI, or you want to configure this as I2C. All this can be configured with this jumper. You need to use a solder and perhaps solder the bridges. That's what I hope. I've never tried it, but looks like that's what it is, whether you want to configure I2C or SPI. And they give you the complete tabular data and how each of these pins would be used based on different configuration in here. This is a Waveshare board and 1.3-inch, and you can see it's got 8 pins. Though there are 8 pins, you should note that there's a VCC here, ground. This pin, NC, stands for no connection. You don't connect it to anything on your Raspberry Pi Pico. And why is this pin exposed? I have no idea. So I to be honest, I don't know if there's anything being marked here about the NC pin. No, nothing on the table, and no idea whatsoever. Maybe for symmetry, for the purpose of symmetry, they would have kept this NC pin for maybe compatibility with certain boards, perhaps. So normally you don't connect it, and so this pin is ignored. You just need to ignore this NC pin. The D in is actually SDA. What you see as D in is equivalent to SDA and some other boards, which means it's a data pin, serial data. That's what SDA stands for. Here it says data in, so it's all the same. And out of which you have the CLK pin. The CLK is labeled as SCK in other displays, which I just showed you a while ago. It's the same as SCK pin. And you have a CS pin, that's chip select. Then you have the data or command or DC, and you have the reset pin. So these are the 8-pin setup that you have here on this display. By the way, this is a 1.3-inch display, but you can get the same display in slightly smaller size, which you can see here. It's almost similar. Both are from Waveshare. When this is also Waveshare board, the pinouts are exactly the same. The size of the display panel, however, is smaller. It's a 0.96 inch here. This is a 1.3-inch display. So this 0.96-inch display, you can see it's got the backside. It's got a very similar table like you see on the 1.3-inch display, and you can see the Waveshare logo here. So obviously it's coming from Waveshare board. So these are the pin configurations that you find for the display. Now I'm going to show you how to actually wire this up on your Raspberry Pi Pico and how do you actually test it. Well, in order to do that, I have pre-connected the wires on the Raspberry Pi Pico to save time. So I don't want to do it in a video. Most of you will find it boring to watch that, me wiring things up. So anyways, so I have one of these Raspberry Pi Pico board here. And let me just reduce the zoom. And this is an A-Fly DIY board. This, I just bought 2 of them 2 days ago, right? And I just tested it. It looks good. It's a complete drop-in replacement for your official Raspberry Pi Pico. So if you have an official Raspberry Pi Pico that looks like this, which you can see here, I have another breadboard in which I have the official Raspberry Pi Pico. I have actually used an A-Fly DIY board, which is exact replica, almost, right? Apart from the fact that, let me just show the side. You can see that there are two buttons in here. You have the reset button, and you also have the, you have a reset button here along with the boot cell button, right? In all of these, I have flashed MicroPython firmware. If you have not figured out how to put MicroPython, look up my other video. I think if you look at my video playlist for the embedded and IoT kind of videos I'm doing right now, you'll find a video where I actually focus on flashing MicroPython on Raspberry Pi Pico as such. So you can look up the video. So I have flashed MicroPython on this, but we're going to install the library for displaying. And let me tell you about the pin outs which I have configured in here. So first of all, you can see that this particular pin, the last pin that you see here on this. So if you start looking up the Raspberry Pi Pico, let me just try to reduce the zoom a little more so it's slightly more better. Yeah. So when you look at the Raspberry Pi Pico in here, you have the micro USB connector in this place, right? And this is pin 1. You can start counting from pin 1, 2, 3, 4, all the way to pin 20. Pin 21 starts in this corner and it ends at pin 40 here. So it's like pin 1 to pin 20, pin 21 to pin 40. It's the, you use this direction for counting the pins, right? From here, all the way go up. Now here's the thing. This pin 40, if you look up from the pin out diagram, this is supposed to be the, V bus pin, which connects to the micro USB's positive supply voltage. So I have run a wire from here to here to the positive rail of the breadboard such that you can also see another red wire here connected on this rail to this side. This is where the VCC would go when I connect the display in a while. I'll do that in a while, just hang in there. So this positive rail is actually connected from here all the way till here, right? So if you connect the display in this place, so if I'm just going to put this display, it's meant for this display. If I put this display in place here, like so. Yeah, just trying to show you, right? You can see that this is a VCC pin on the display, which connects to the positive of the power supply coming from the micro USB through this Raspberry Pi Pico. You can either connect to VBus or you can also connect to the next pin, which is the VSys pin. The next immediate pin is VSys, which is nothing but a regulated supply coming from the Raspberry Pi Pico. But if you're using a breadboard power supply, that's where it will be connected to, right? You can also see that from the pin out, if you, I have shown you in my previous video about the pin outs for the Raspberry Pi Pico. I'm just going to recap that. This particular pin, I left the 39th pin, which is the VSys, but I'm using the 38th pin, which happens to be the ground pin. The ground pin is connected to the ground line, which also goes on to this side, where you see a black wire connected all the way to connect to the ground to the display. And then if you look at the Raspberry Pi Pico in here, there are these side of pins. The GPIO pins is what I'm using. I'm not using anything on this line. If you can observe that, nothing is connected here. I'm using only a couple of pin connections on this side. And what are those pin connections? Just hang in there. I'll just try to get a sheet to show you. Just one moment. Yeah. So you can see that this is the pin layout, right? So if you see the Raspberry Pi Pico in here, pin 40, I've connected to the red wire, which you can see here. And I've not connected pin 39, but if you want, you can connect pin 39 if you're going to be using breadboard power supply, for example, right? And I've used the ground pin here, connected to black. And you can see on this corner, which you can see here, this corner, let me zoom this a little more to show you better. You can see that pin 21, which is GP16, okay? You can make a note of that, GP16. We'll be using this in the program. We need to know these numbers. GP16, GP17. I'm using this pin, GP16, GP17. I'm using, I'm not using GP18, I guess. Am I? Oh yes, I'm using GP18. I'm using GP19 and also GP20. So I'm using like 5 connections from this side, right? This makes up totally 7 connections on the display. The display has totally 7 connections, though it's an 8-pin display. 1 pin is no connection. There are 2 pins for supply, which is VDD and ground. And there are 5 more pins. And those 5 more pins are connected through this side, in this side, right? So if you see this particular GP16, you can configure this as an SPI interface because you can also see an SPI clock here, right? Not SPI clock, sorry, SPI RX, right? I'm connecting the reset onto this particular pin. Reset can be connected anywhere, but I'm just choosing this for the convenience. And this is acting, this will be connected to chip select or CS pin. The SPI 0CX, right? all of these represent SPI controller 0. You can see it shows up as SPI 0 here, SPI 0 in this place, right? So basically you can see that this is a CS, this will be connected to the CS pin of the display. And I'm not using the ground because I'm using the ground from this side anyways. And you can see that the other pin that is there is an SCK pin. This will be connected to the clock pin, right? The CLK or SCK, whatever you find on the board. And this one, the SPI TX, will be connected to the data pin or the DIN or SDA pin. So if you either see a label called SDA or DIN, this is where it goes to, right? I'm also using GP20, which is a general purpose pin. I'm using that for DC. I'm connecting it for data command, right? So data or command selection. So these are the pin configurations that you can see here. And if I plug this board in the right place, just one moment. You can see that to confirm the VCC is connected, right, to the positive rail connected to the supply, which comes from the RaspberryPi Pico. You can also see that the ground pin is also connected likewise to pin number 39. You can also see that the no connection pin is left not connected. You can also see the DIN pin. You can see, or here you can see a green wire running through all the way till here, which apparently connects to pin number 24. Pin 24 happens to be this one. Let me just bring this to this corner so you can see it a lot better. Okay. You can see this better, right? You can just focus on this side. So you can see that the green wire, which is connected to DIN, goes all the way through here, connecting to pin number 24. It gets 21, 22, 23, 24, right? I think you can see 21, 22, 23, and 24. The 24th pin is connected to this green wire, and the green wire is connected to this side, which is the DIN pin, right? The next pin that you see, there's a gray wire I've connected. I use a gray standard wire. The gray wire connects to clock. The clock goes to the next pin, immediate next pin, which is pin number 23, right? Pin 23. And then you can also see there is another pin which is in blue. A blue colored wire is connected to this next pin, which happens to be is it a chip select? No, sorry. I think the chip select pin is what comes next. Sorry about this. So I can see after the gray, you can see chip select is coming on the next rail, which is there here, which is where I'm connecting a yellow wire, which runs across to connect to pin number 22. The pin number 22 happens to be the CS pin. So it's the CS connection of Raspberry Pi is connected to the CS on this particular display. And you have the DC pin. The DC pin, which you can see, runs across to this blue wire. So I use the blue wire here in this place. I couldn't find multiple lanes. I'm sort of sharing a lane, so it looks a little, kludgy or overlapping. So you can see that I have actually run it across like this, right? So run it across like this. So you can see this. This blue wire is connected to the DC pin, which actually runs across all the way to connect to pin number 26. And pin 26, as you can see here, is GP20. So pin 26 is GP20 that you can see here. So all of these are the wire connections. And the last one, which you can see, is a black wire running across from the RES pin to pin number 21, which happens to be this particular SPI0RX. You can connect it to any other GP pins if you want to. So if you're looking at the DC pin and the RES pin can be connected to whichever GP pins you find convenient. And yes, by the way, I've used this configuration because I found this convenient, but depending on how you design, you can get more creative. You can see that your Raspberry Pi Pico has the same SPI connectors below. That means you can also use the connections below here. Make sure you have the CS connecting to CS, TX connected to DIN, and the RES can be any GPIO pin, and even the DC can be any GPIO pin. Just make a note of that GPIO pin that you're connecting to. And what else? The CLK to SCK and CLK, right? You need to connect to that. So that's what the configuration is. In fact, you can see that you can either use this SPI interface, which is SPI1. Again, the same SPI0 is also available here. So either this, when you connect on this side, that is on this corner, or if you use this side, both represent SPI controller 0. And SPI 1, SPI 0 is repeated. You can see 1, 2, and 3 times. You can use any one of them. You might ask me why they have so many repeated pin connections. Basically for convenience. So it's possible that some of you might want to have these pins connected, the pins on top, right? The pins on top, you want to use it as a general purpose GPIO pins to connect to other devices or other sensors. And you want to use this side for your SPI connection. Or you can do otherwise. You can maybe use this as general purpose IO pin for other sensors, and you can also use this as SPI. So you can mix and choose the way you find it convenient for you, right? So that's why there are repetitions of this SPI connection possibilities and also I2C connection possibilities on a typical Raspberry Pi Pico. So I have made this connection in here. Now, in order to test this, you need a library. This particular display, as I told you, the 8-pin wave share display, if you have this, right? If it looks like this would very likely be using an SH1106 with SPI interface, right? That's what you should use. So I'm going to tell you how to actually run the program across, how to install the library on the Raspberry Pi Pico and use that library and test it across, right? It'll be a very simple program. It will just print a hello world kind of a message, right? So that's how it's going to be. So just hang in there. I want to just switch the screen. Okay, first of all, I'll have to show you from the web browser. So here you can just open up a web browser, or use your favorite web browser, open this, and within your web browser, you might want to just look up this particular website. It is github.com/robert-hh/sh1106. So I will share the link to this particular website in the description in this video. So you can just head over to this website and you'll find this GitHub link, which was driver for SH1106 display for MicroPython, obviously. And now all you need to do is that you can click on this sh1106.py. Just click on this and you'll find the Python program loading. You can see this. This is a MicroPython driver for the SH1106 display controller for this OLED display. So this is it. You need to just copy this into your Raspberry Pi Pico. And the way I'm going to do that is quite straightforward. Just click on the raw, which you see here, the raw link that you see here. Click on raw mode. This opens up in raw format. You can also click on download the code, unzip the file, and copy the .py file. All that can be done. So easy way. If you're going to be using something like Thonny, I think this is just much more easier. Just open this file and in raw mode. And once you're in the web browser, just you can use Control A to select the entire text inside this window. Type Control C to copy it onto the clipboard, and then fire up the Thonny editor. Open Thonny editor, which I already have opened in here. First, let me connect the display also. Okay, so okay, I'll do that later. So I can actually create a new file, open a new file, and save this. Save this in here. So you can actually see that when you open up in the Thonny editor, the code shows up in slightly larger font than mine, so it's quite good. You can see, you can read it. It says MicroPython SH1106 OLED driver. This driver works for both I2C and SPI interfaces. So if you're an SH1106 with 4-pin or SH1106 based driver with 7-pin or 8-pin, it works for both of them, right? And it shows all the copyright, all the details. It's an open source project. Anyways, it's nice. They also give you some ideas, design ideas on how you want to connect it to your actual boards. And here they show you information for the ESP8266. So if you happen to use an ESP8266, this might give you some hint on what all data pins can be connected for testing, right? What pins can be connected. And in fact, you can see that CS pin they claim is optional only if only connected device, and otherwise you can leave it off. They don't give you much information about how to connect it on the Raspberry Pi Pico, because I think this particular program was created primarily for ESP8266 on MicroPython, but it works perfectly fine with Raspberry Pi Pico, right? Because it's a pure Python project. So here they give you some information on how to initialize the display, and there's an example on how to test this. There's an example test program, which you can adapt it to your needs. The only thing that you need to take care of is the pin numbers, the GP pin numbers that you need to assign, which I will show you in another program which I've created. And also below you can see a couple of things like register definitions. There's a class, there's a top level class which is SH1106. You don't want to be using this. This is like the base class for the actual implementation. The actual implementation classes or the subclasses which you find below. If you're going to be using the I2C interface, you need to instantiate this class, right? Which is inheriting from SH1106. You can see there's a init method which will take all the constructor parameters, and you can also see what constructor parameters you can pass. You can pass the width of the display, the height of display. You can pass the I2C connection, what I2C controller you want to be using. You need to instantiate an I2C interface for that. I will show you how that is done in a while. You also have something called RES is equal to indicate what is the RES value, which pin is the RES connected to. I think it's optional here. You can leave it to none. If you just have a 4-pin display, it will not have an RES. The address is set to 0x3C, which I believe should work for most of this display. But if you happen to have a display that does not show up in I2C scan with 0x3C, then you might need to change the address when you're calling this constructor, right? You can pass this constructor parameter. You can also specify the rotation and whether it has an external VCC supply and all that. So all these are constructor parameters which are there here. And it shows write command and all these are the different methods being implemented. There's also an SPI based interface which also takes width, height, the SPI device, the DC pin, the reset pin, the chip select pin, whether you want to rotate the display. This displays can support rotation to 90 degrees or 270 degrees or 180 degrees. You can rotate in different direction. So if you make it upside down, you want to flip it horizontally and all that, you can do that kind of rotation. And they're supported in here. So you can specify the rotation value. If you leave it as 0, it'll be the default. It'll show it widthwise, right? These are the classes that you see. That is 2 important classes to look for. One with SPI interface, one for I2C interface, right? So what I'm going to do now is I'm going to connect this board and test it, right, with the SPI interface. So let me just clear my desk a bit. And I need to locate an USB connection. Yeah. Okay, let me just switch my scene. I'll switch to the screen in here or this one. So what I've done is I've just connected this to the micro USB. I turned it upside down so you can see all these connections I showed you last time. I showed it to you like this, right? But it looks like my micro USB. I think it's fine. I think this is actually the display will be upside down. So it's fine. I'll just leave it at this. So there's all the displays connected, as you can see here. I've connected a micro USB, and the next thing I want to do is I will launch, check this in MicroPython. I'll click on the stop. I think if at all you have to configure access to MicroPython that's running on the Raspberry Pi Pico for the first time through Thonny Editor. I guess you know how to do that. You can just click on Tools, Options, Interpreter, select MicroPython for Raspberry Pi Pico. If it's got something else, and make sure the port, you should be able to see something like board CDC if you're running on Linux, or if you're using Windows, you might see something like, say, board interface mode, COM1 or COM3 or COM5, whatever that number, the COM port. Select that port, and once it's done, click on OK. If all goes well, you should see a MicroPython shell prompt right here. Now, this particular file, which I just copied into my Thonny interface that you see here, so I'm just going to, save this file, right? So just one moment. I'll just switch to another scene for this. Yeah. So I'm going to save this file onto the Raspberry Pi Pico. To do that, you click on the File, Save As. If your Raspberry Pi Pico is connected and the MicroPython is detected, you will see this dialog box. Okay, it's not showing the dialog box again. I'm so sorry. Okay, I need to switch my scene. I think I need to put a go to full screen mode, I guess. Hang on one moment. Yeah, you can see that. So you can actually see that it says where to save to. This happens when you actually click on File and click on Save or Save a copy, right? You can say File Save. First time you try to save it, it'll ask you where to save to. Select Raspberry Pi Pico, and once you select it, it shows up the contents of Raspberry Pi Pico. It looks like on the Raspberry Pi Pico board, I already have these files. I was just doing testing before I made this video. So obviously, this file is actually being saved already on my machine, but you want to save it by typing this name, SH1106.py. Do note that the file must end with .py extension, and I'm using all small letters, and that's the common convention for naming the modules. Okay, I'm just naming it as SH1106.py. This name is very important. Whatever name you use here, remember it, and make sure you don't use any special characters in the name because you cannot load them up as a module, right? That's something that you should be aware of. So you can just save this in this file. It'll ask me to overwrite it. So fine, I think you can overwrite it. Now the next step is I want to test this board, right? So in order to test this board, I'm just going to go to the other scene in here. Yeah. So this board is laid out in this top window that you can see. Okay, I'm just going to move it across like this. I'm going to turn it upside down, so maybe this might look a little stable. Hopefully, yeah. All right. And by the way, most of the display might come with a small tab here. Some of you might wonder what this is. There's nothing but it's a screen cover, so you can just remove it off in case you're not worried about scratching. So this is basically it'll act like a scratch protector. It's just a small plastic coating film that's there. So I'm going to leave it on because I think I put my displays here and there, and I don't want it to be scratched. So I'm just going to leave it on. I'll just put it later. Okay, let it be around. All right. So you can see the display is clean, looking clean now, right? Now what I'll do is to test this display out, I need to know the pin connections which I made. I'm going to use that. And first thing in the MicroPython shell, I can say from machine import pin, comma, because it's a 8-pin display, it's going to use SPI. So I'm going to use SPI here. The machine module in on MicroPython for Raspberry Pi Pico provides support for SPI and I2C interfaces, right, as classes. So you can just use it as is. Yeah. And now what you can do is you can actually use I2C. Oh, sorry. I'll call OLED underscore SPI. I'm going to name this as a variable. You can give any name you want. This is just a variable name. I'm just choosing the name as OLED SPI is equal to create a new SPI interface. Now the SPI class takes a lot of parameters. You need to specify which pin acts as the SDA pin, which pin acts as the CLK pin, mainly, right? So let's look at the help right here. If we just, maybe if you want to look up the help for this, you can check it up on, okay, I think I need to switch to the screen scene. Sorry about this again. Okay, so let me just go to micropython.org. You can look up the document. You can look up the docs in MicroPython, and here in docs you can search for SPI. It gives you all the SPI classes, and the SPI interface will take different parameters. If you're going to be using an ESP8266, it'll take slightly different parameters if you're going to be using a Raspberry Pi Pico. So for Raspberry Pi Pico, select RP2, and this Raspberry Pi Pico's reference. They will tell you all the nuances related to Raspberry Pi Pico, the timers, pins, and GPIO, programmable IO, UART, PWM, and all of this stuff. And here's where you can see the SPI interface, right? What are the parameters you can pass? There are two kinds of SPI interfaces. One of them is a software SPI interface, which you can configure on any GPIO ports. But then there is also a direct hardware SPI busted set here. So if you want to be using SPI, you can just say from machine import SPI, and SPI is equal to SPI of, you can specify which controller you want to use, whether it's SPI 0 or SPI 1. So you can select that. And in our case, because I've connected this to SPI 0, right? As per this particular display, which you can see is on SPI 0. So I'm going to select that. And what is the baud rate? You can set the baud rate accordingly. I'm going to start with something very small. So I'm going to start with something like 2 20 megahertz. So you give it to 80 megahertz or whatever speed. So sometimes the display might not work out if you put it to very high baud rate. It depends, right? If your display can support high speed, you can try with high frequency, otherwise you can reduce it. And there's polarity, phase, bits. I'm not sure if you need to pass these parameters. The only thing that you need to pass is the SCK pin, and you may need to pass the MOSI pin. MOSI stands for Master Out, Slave In. This SPI has the concept of master and slave. Basically, the Raspberry Pi Pico acts like the master that's going to generate the output, and the display controller on the OLED will act like a slave that's going to take input. So that's why we say MOSI, right? We say what's a MOSI pin, which is equal to whatever pin is connected as SDA, right? Or the TX pin of SPI is what you need to pass this in. So I'm just going to just pass these two parameters. I think it's just be fine. If at all the master is going to take input and the slave is generating output, then you need to also provide MISO, which does not happen on this display. It does not generate any data back to the Raspberry Pi Pico. So you don't have to worry about that, right? So I'm going to select this parameter. So I'm just going to use the same parameters in here. So let me just go back to this screen and just going to type OLED SPI is equal to SPI off. I'm going to select SPI controller 0, and then I'm going to type called SCK, right? Yeah, SCK is the parameter you pass. I type SCK is equal to, I can just provide which pin is connected to the clock. Well, on this particular connection, I have used the clock as GP18, right? It's actually GP18. So this is where the clock is connected. The clock is connected to GP18. You can see that. So it's connected right here. So you can just see that the clock is the gray wire that's actually connected to this particular pin, which corresponds to GP18, right? So I'm just going to use that as the connection. So this GP18, it's a GP18. Yeah, here is GP18. You can see that right here. It's connected to this particular pin, right? That's pin number 24. So I'm just going to use pin of 18. And I have the GP19 that's connected to the MOSI pin. The MOSI is master out, slave in, that connects to pin number 19, as you can see here. So you can see that the D in, the green wire, you see where it runs to, it connects to pin number 24. The pin number 24 on this particular sheet, pin 24, corresponds to, okay, pin number 25, sorry, I think it's connected to pin number 25, I made a mistake. Pin number 24 is connected to the clock. Pin number 25 is connected to GP19, which you can see here, SPITX, right? As you can see here. So I'm just going to use that pin here. Sorry. One moment. I think the mouse has selected something in here. Okay. Yeah. Oh, okay. The connection is lost. I'm sorry about this. I think I just snuck this back. This particular cable is a little loose. So let me do one thing. I have the program ready. I'll just open the program and show you. So it's much more convenient for this video. So let me just reconnect it back. I think this cable has a problem. It has loose contact. So I think that this has been disconnected. So never mind. So I'm just going to open this program. I think it's there on the Raspberry Pi Pico itself. Let me just open that. So I've just switched to scene in here, and I'm just opening a file from the Raspberry Pi Pico, and one of them is a SH1106, which already open. I'm going to use the SPI variant here. Yes. So I think I've also written some comments. I'll be sharing this code. I'll be sharing the link to this code also, the test code, which you can use and test it if you use an exact similar pin configuration like mine. But then if your pin configuration is different, you can customize them accordingly, right? So you can do that. So here I can see that you can see a ground is connected to pin 38 and VCC to pin, I think I've used not 3.3 volt. I've connected to pin 40. So I'll make that small correction in here. And the SCK pin is connected to GP18, that's pin 24, and the SDA pin is connected to pin 25, which is GP19. Like you can see that GP18 and GP19, right? And you can also see that the RES pin is connected to pin number 21, which you can see here. And the DC pin is connected to pin number 20, and the CS pin to pin number 22. So it's all connected accordingly, right? And then you can see that I've used from machine import pin, comma SPI. If to test it, I can just copy line by line and show it to you right here so you can see how the display works. I can just copy this line. These two libraries are part of MicroPython, nothing to be copied. It's part of MicroPython standard library. But this particular code that you see here, from SH1106, I said import SH1106 underscore SPI. We just copy this code. Remember this file that we sort of copied from this website, right? We selected it all, copied it, and we pasted it in this page, right? This page. So this is the code that we copied from the web browser in this place, right? And I want to import that too. So I'll just copy this line. So it's basically going to load all these classes from these modules. So these classes are all loaded. Now the next step is I'm just going to instantiate the OLED instance by calling it SPI underscore OLED. It's just a variable. You can call it any name you want. So I just call it SPI OLED is equal to SPI of the 0 indicates the SPI 0 controller. That's what you see. This is SPI 0 controller, right? In this case, this connects to SPI 0 controller, right? This part. And then this is a baud rate at which I'm trying to try out. You can increase the baud rate if it works. Sometimes you see the display can get garbled. You can reduce it, right? Basically, reducing the baud rate will make the display a little slower. So if you're trying to do animations, it might have a lot of frame skips and all that. So it may not work out very well, right? Okay, the connection got lost one more time. No problem. Let me just try to stop and restart. It should work. So I think I should not disturb this particular board, right? So I'll just copy these lines again. And I'm just going to copy this line too. And as you can see that, I'm just instantiating an SPI class for SPI interface 0, controller 0. There are two SPI controllers in the Raspberry Pi Pico. I'm selecting SPI 0 here. I'm setting the baud rate. The MOSI pin is pin of 19, which is the GP pin connected to SDA or D-in on this particular display. And you can see that SCK is nothing but the CLK pin, which is pin 18. So we need to just instantiate with these parameters. That should suffice for this now. And then this is where things get interesting. I can just say display is equal to, this can be another variable. I just call it display. You can name this variable to whatever you want, is equal to SH1106 underscore SPI. So this SH1106 underscore SPI is a class that provides the SPI interface to connect to this display controller, right? The SH1106. I'm setting the width to 128, height to 64. SPI is equal to the SPI OLED variable that I'm using on top, and to what connection the DC pin is connected to pin 20. We can see that pin 20, right? And RES is connected to pin 16. When I say pin 16, these are the GPIO pins, remember, right? So the GPIO connection, the GP pin connections is what I'm mentioning here. The CS pin likewise. I set rotate to 0 and delay to 0. This rotate and delay, you can ignore it for now. So basically you can do some rotation on display. If you want to make it sidewise, like vertical and all that, you can make that configuration. Let me copy this line. It's quite lengthy. In here. So you can see it's got width, height, SPI, DC is equal to what pin is connected to DC, reset, that's RES is equal to that's reset pin, what pin is connected to reset, what pin to chip select, rotate and delay. All the parameters have been set here. If all goes well, it just comes back to the prompt. If you get something like E timed out or so on, there's some problem with your connection or the display controller is not SP1106. That is something to note, right? So normally the display should come up without a problem, without any errors. Once it's done, we can power on the display by using display.power on. If your display controller is not based on SH1106 driver, sometimes when you say display.power on, you'll see some garbage coming up. You'll see some random pixels turning on. This means that this library is not compatible with the display. That's what you should note, right? Sometimes it's possible that if you got your pins wrong, even that can happen, right? So that's something that you should watch out for. So once your display is powered on, you can actually try display dot text off. You can put any string you want. I'm just going to type it worked. And this display.text takes a string followed by the coordinates, the row and column. So I'm just going to use, let's try 2, 2. Second row, second column, right? Start from there. The top left corner of that string will be starting from second row, second column. 2 pixels left, 2 pixels top, right? Well, nothing comes up. Not yet. You might have to call display.show here. And if it works well, you can very well see it shows that it worked. Right? This will remain as it is. You might want to fill with 0. If you want to clear the screen, you can actually say display.fill of 0. And then you might want to call display.show one more time. It's always this technique. You say display.text or display.fill, display.rect. You can use a couple of methods which are there. If you look up the actual base class, the SH1106 base class, you'll find a lot of methods available. You can invoke those methods. But to show that screen, you call display.show. Once you're done with it, if you want to power off the display, you can also call display.power on. That's it. So now we know that this display works, and we tested it with the SPI interface. You can now connect sensors like the basic thing you can do is connect a DHT22 or DHT11 sensors and read the temperature, humidity, and you can display that on the screen. So you can use any GP pins to which you can connect them, and you can display it. So you know how to display something using the SPI interface using SH1106, which based on an 8-pin OLED display. The next I want to show you is the one with I2C, right? And the I2C has two configuration. By the way, this display, I use a 1.3 inch display. I can remove this display completely. I can remove this display. It's a little risky to do it when it's plugged on. I'm going to disconnect it. I'm going to remove the display altogether. So let me just change the scene. So I'm going to remove this display this time. By the way, it can be more snug on the motherboard. So if that's the case, you might want to use some tools like these. Make sure you use a plastic tool like this. If you use some kind of prying tool, make sure it's made of plastic. Don't use metal. They can damage the components. Okay. So don't use a metal screwdriver. So be careful when you use a metal screwdriver. Use a plastic one, which is actually much safer to pry it. And yes, let's remove this display. I'm going to just drop in replace another display which I have here, which is, yeah, the slightly larger one. You can see that. I just removed this display that was there. I removed it. I'm going to use the slightly larger display, which is also the waveshed display. It's all the same. The pinouts are same. It's a drop-in replacement. You can actually plug this in. I'm going to do the same thing in here. I'm going to plug it in correctly to the positive and the negative. Yeah. So plug this display in this time, which is a 1.3 inch display. This one is a 0.96 inch display, right? Which I plugged in earlier. So I'm just plugged in the 1.3 inch display. And I'm going to connect this back. And I'm going to run the program again. Okay, I'm going to reconnect on my Thonny editor and run the program. So you can see that. And just click on the stop button to restart connection. You can see the micropython prompt comes up if the connection goes well. And then after that, you can run this program. This test program, I wrote it independently, right? I just copied each line and I typed it off in the MicroPython shell. But this time, I'm just going to run this program as is. So this will display the same text. You see, it shows it worked. It shows the display. After about 10 seconds, it clears the screen, shows and powers off the display. right? So I'm just going to run this program. I put this in a file, save this as SH1106 underscore SPI test.py. I hope this would work. So let's click. I'll just save this file and click on the run button. Well, it worked. You can see that right here. Yeah, it powers off in 10 seconds because I put a sleep of 10 seconds and afterwards it powers off. So this both are exactly the same. So you can use the same program, same library to work on the WaveShare boards. But however, if at all you have a 4-pin display, it's possible that the display can be based on an I2C or an SPI interface, right? So I'm going to try both of them at this moment. Just one moment, please. So here is another display which I have here. I think I removed the Raspberry Pi Pico. Let me just connect the Raspberry Pi Pico from one of them which I have here. Let me just remove it. All right. So I'm going to plug the Raspberry Pi Pico board in this display, in this breadboard in here, and I'll tell you how the wiring is done. This is basically using a 4-pin display which uses I2C interface, right? So I just plugged in the Raspberry Pi Pico on this particular board, and I'm going to show you how the connections are. So, well, by the way, let me just zoom this up a bit. And let me change the scene. Just a moment, please. Yeah. So this particular display, I figured out it's actually based on an SSD1306. It's a SSD1306 display. What is noticeable is that the ground pin comes first. Then there's a VCC pin. And then there's an SCK and SDA. Now the connection goes this way. The ground pin, obviously, you can see the ground pin in here. You can see on the top, you can see a black wire connects to a negative rail. This particular breadboard is I've put it in the reverse side. So you can see the negative rail comes on top and the positive on this side. Ideally, what should be connecting it like this in this side, where the positive comes on top and negative below. I mean, I'm not going to be using breadboard power supply, so that's okay. Something to note, right? If you're going to be using breadboard power supply, you should be a little careful about the positive negative directions. So you need to use you need to wire the wire on the breadboard accordingly. So, but in this case, it's okay because I'm going to be connecting using the micro USB port. So shouldn't be a problem. So you can see on this particular Raspberry Pi Pico, we can see the pin 40 is connected to the positive lane right here, the positive lane. You can see the positive lane in this place. It runs across to connect to this side, with a positive lane on this side, which actually connects to the VDD, right? It connects to the VDD at this point here. So you can see the ground to ground and pin number 40 of the Raspberry Pi Pico to VDD. And there are just 2 pins here. As you can see here, the next pin is SCK pin. The SCK pin is connecting to the yellow wire that is on the same lane, which connects to this pin, which goes here. And this pin, if you just see what it is, let me show you, because I'm going to be using an I2C interface. If you're planning to use I2C interface, so you can use any one of these, right? You can see I2C 0, you can see I2C 1, I2C 0 repeated again here. So you can use any one of the pins. I chose the corner 2 pins, which is very convenient. It's very close by. I chose that. So if you look at the pin number 21 of this, the pin 21 on the Raspberry Pi Pico on this corner, yeah, the pin 21 on this corner, right? Basically, this can be configured as I2C0 SDA. And the pin 22 can be configured as I2C0 SCL. So SCL is nothing but clock, SDA is data. So configuring this is pretty straightforward. As you can see, what I've done here is that what is labeled as SCK in here, there's a yellow wire connecting to it in this side, which runs across to pin number 22, right? Pin 22. And pin 22, as you can see from this board layout, it is the SCL pin. Whereas the SDA that you see here, that you can see a green wire being connected to the SDA. That runs across to connect to pin number 21, which is nothing but the I2C SDA for I2C0. That's it. So you just have 2 pins from here connected to this and so on. By the way, if you, for simple connections like these, using a breadboard can be avoided. You can use jumper wires like these, right? Just that this is a male-to-male jumper wire, but because both of these have headers, you might want to use a female-to-female jumper wire to connect them across. So you don't even have to need a breadboard. Because you're only talking about 4 wires, you can use a 4-wire jumper cable like this. This got a male header. You want to get one with a female header. Do I have one here? I guess not. No. Just one moment, please. I'll just be back. I'll show you that. You need jumper cables that look like this. So you can just connect it to this board, right? If you have this board in here, you can just connect these headers right through this. The only thing is you have to make sure that you know the coloring of the wire, right? Sometimes people want to use the red wire for the positive supply, that's VCC or VDD, and they would use the black wire for the ground. So those are things we should keep in mind. But if you don't get the right colors up, it's okay, as long as you remember the colors. And of course, you just need 4 pins. So I think this wire has multiple pins. It's got 6 pins, but you can just connect 4 of this, and you can tear out the others if you want to. You can connect it like this, right? And you can connect it to the other end, or other end can be connected to a Raspberry Pi with headers without having to connect it on breadboard. Maybe I will show you that if I have time. But anyways, for now, I've just used the breadboard because it's nice to lay things on the breadboard, and you can add more devices and more sensors later on and improvise your circuit, right? And program it. So when you have this connected in this configuration, all the 4 pins are connected to the Raspberry Pi Pico. The next step is obviously installing the driver for this on this Raspberry Pi Pico, basically the library for this. As I mentioned, this uses an SSD1306, right? This configuration. So I'm going to use that library with I2C as such. So let me run this across. Let me just change the scene. I need to connect this to the micro USB here. All right. So I connected to the micro USB, and let me hit on the stop button on the Thonny and see if it's the shell can reset and show itself. Yeah, it's shown up. It's got a slightly older version of MicroPython. It's 1.20. The latest edition is 1.21. This requires a firmware update. You can ignore it. It's going to work though. So what I'll do right now is you need to, because it's based on a SSD1306 chip, right? That display controller, you need to download the file for that. In order to download SSD1306, you need to head out to the web browser. So the web browser, you might want to go to this particular website, which is, hang on 1 minute. Yeah. 1 moment. Yeah. You might want to go to github.com/STLEHMANN/micropython-SSD1306. So I'm not sure how to pronounce this. It's just an ID, so you can just go to it. I will be sharing the link to this particular URL in my video description. So once you head out to this particular URL, all you need to do is you can this particular library can be installed via MicroPython package manager. I have tried it once and it didn't work. So I'm not sure. Maybe it's got to do with my network connectivity or my ISP's DNS. I have no idea. It didn't work. But it's just a single file. So it's pretty straightforward to just go to this particular URL directly. And once you're in the GitHub URL, just click on this link, which you see here as SSD1306.py. Just click on this link and the source code for this opens up. this is the library for accessing this controller, right? SSD1306. And as usual, you can click on the raw button in here. Once you select raw, you can see the source code is shown in a format that you can paste it in your Thonny IDE. So you can just use Control A here, Control C, open up Thonny. Yeah. Once Thonny is open, you can actually create a new file. I think I already did that. So just create a new file and then paste it here. So once you paste a new file, the next step is you need to save this file into your Raspberry Pi Pico. You need to save it in Raspberry Pi Pico. To do that, you can click on File and you can click on Save As, Raspberry Pi Pico. And make sure this file is saved under the name SSD1306.py, like you can see on the screen. It is SSD1306.py. The file is already saved here. I think I already have that file on my Raspberry Pi Pico board already. So you can just select that. And this is what you see. You can see there's a class called SSD1306. Looks like this particular library is available in MicroPython standard library too. I need to cross verify because earlier it was not there. Maybe they added this in the standard library recently. That's what I heard. So they have provided Spring Buffer and everything as such. So they have created this class is, I think there's just a fork of that particular library and this sort of works, right? So this has the SSD1306 base class and you can see that it's got both the I2C interface for this and it's also got an SPI interface. But because you're using a 4-pin display connected on the Raspberry Pi Pico, so we are going to use an I2C based connection. The I2C connection, I2C class, the constructor takes only the width, height, the I2C chip, I2C interface, and then the address. You might need to change the address accordingly, right? For if the address is not the same as what you see it listed in here. So now to test it out, I have another file which is very similar to the one which I showed you earlier based on SPI. It's already available in the Raspberry Pi Pico. I'm just going to open that file. Yeah. So here you can see the same. You can see I'm using from machine import pin, comma I2C. This is from time import sleep is for a delay, which I'm using here, after which I'll power it off for after 5-second delay. I can increase it to 10 seconds if I want to. And you can see that from SSD1306, which is the .py file, which I just saved in the Raspberry Pi Pico, that is going to be used as a module. So from that particular file, from that module, import SSD1306 underscore I2C, which is the same class that you see here. Now, this class is instantiated. You can see that. First, before that, you can see I2C is equal to create an instance of I2C. You can see that it's connected on I2C controller 0, right? One moment. Yeah, here it is. So it's connected on I2C controller 0. This is I2C 0, which you can see from the label, right? It is I2C 0 here. And that's where we have connected our display. So you can actually see that it's connected to that particular point. So let me just leave the display alone here. Yeah. And you can see that it's I2C of 0. The SCL pin is connected to pin of 17. I think this GP pin 17 corresponds to this particular pin in here. This you can see is GP17 and this is GP16, right? GP17 is the clock pin, GP16 is the data pin. So you can see the same configuration in the program in here. So SCL is equal to pin of 17, ESD is equal to pin of 16, and the frequency, I've set it to low frequency. You can try increasing and checking it, but I realized that this frequency works without a problem on this board. So I stuck to 20 megahertz, right? So yeah. And then you can see OLED is equal to, I call it OLED, but if you want, I don't find this naming convention good. I just wrote it, but I'll just change it off. I think I'll call this as I2C OLED instead. And this, I'm going to call it as display. Proper naming conventions will avoid confusion, right? So I'm just going to call it as display.power on. Yeah. Display is equal to, I say SSD1306 underscore I2C, width, height, and only thing that you need is the I2C object passed on as a third argument, which you see here. So you can call it as I2C underscore. By the way, when I'm using the constructor expressions in here, you can see me using keyword arguments. I call it as width is equal to, height is equal to, I2C is equal to. It's not really compulsory. You can pass it by position. But by using a keyword argument, you're trying to make it more readable. So you know exactly what 128 is, what 64 is. And on the I2C interface also, you can see what is pin of 17. I know it's an SCL pin by seeing SCL is equal to, right? So this makes it more readable. So it adds in readability. So I recommend it use keyword arguments so your code is more maintainable, right? So you can use I2C is equal to I2C OLED and display.power on, after which I can actually use display dot text of any string that you want and the row column coordinates where you want that to be displayed. If you want, you can try 10, 10. It comes up somewhere, not in the topmost corner, but somewhere in the middle. So let's see that. And you can try display.show. After about, I'm going to make a 10-second delay here, put a sleep of 10 seconds. That's coming from the time module on top. And it's a display.fill of 0. This will clear the display. And I'm going to use display.show. And then I'm going to use display.power off. That's it. So I'm going to run this program and we're going to see what happens on this display. Let me zoom this up a little more so you can see this screen better. Right. So click on the run button. Yep. You can see that it printed, it worked. You can see right here, right? So that's it. So this is how you can actually program on SSD1306, which has got a 4-pin display. The final one I want to show you is there's another 4-pin display which I have, which happens to be a 1.3 inch 4-pin display. This one, right? You can see this right here. This 1.3 inch 4-pin display. But this is based on an SH1106, but using an I2C protocol. A small variation, right? Earlier, we used the SH1106 with the SPI interface on the WaveShare boards, but you might also get a 4-pin display, which is using an I2C interface, but the chip is based on SH1106. So I'm going to show you how to use this one. It's exactly the same. The only thing to note is that note the VCC and the ground connection. In this display, as you can see, the first pin is ground, the second pin is VCC. But on this display, however, the first pin is VCC, second pin is ground. So you should be a little careful about the wiring. So make sure you wire it up accordingly. The wiring might change here and there. But this is based on SH1106. I have that, I think, connected on one of these boards. So I'm just going to plug this all in this board and I'm going to show you. Let me just recycle this Raspberry Pi board. I'm going to remove it from here. And yeah, let me just change the seat. Yeah. So I'm going to remove the Raspberry Pi from this board. Okay, let me not disturb the display. Let me remove the display off. All right, done. So I've used this board. It's all the same, right? The connection is same. I could have just flipped the wires in the earlier board, but I thought, let me keep different versions of them. Yeah, one thing to note is the Raspberry Pi Pico might not go easily inside these MB102 breadboard. So you might want to apply a little bit of pressure. So as you start plugging them, removing them from breadboard, it gets a little loose. Yeah, it works after that. However, I've seen that the ADI Fly board goes perfectly fine on this breadboard. No struggle required. On this, I had to literally struggle pressing it for the first time, but this just goes without a problem. right? So anyways, so here, same thing. I've just connected made the connection in here exactly identical to the previous one. Just only thing is the VCC and ground is interchanged, right? You can see that the VCC pin from the Raspberry Pi Pico, which is pin 40, runs across a positive rail. The positive rail is on top this time on this breadboard. It goes to this positive, this goes to this red wire that is there here. This connects to the VCC pin in the side. Let me just make sure that I don't have a problem with parallax because it's on the side. I'm just going to ensure that it's all correct. Yeah, everything is in order. So sorry. So you can see that the red wire is actually connected to the VCC pin that's there here. The black wire is connected to the ground pin, which again goes to these ground rail, which is there here, the negative rail here, which connects to pin number 38, right? Which is this pin, the third pin that is there here on the Raspberry Pi Pico, which is the ground pin. And there are only two more wires to be connected. As usual, you can see the usual suspect is that you have a pin which is labeled SCK. And you know where the SCK should go. The SCK should go to, you can see there's a gray wire connected to SCK, which runs across to pin number 22. Pin number 22, which you can see here. So pin number 22, you can see a gray wire that connects to SCK in this place. And the SDA pin, that is the last pin that you see here, the fourth pin on this particular display, has a green wire running across connecting to pin number 21 on this particular board. And as you can see from this particular connection again, just to recap, if you're going to be configured as I2C controller 0, this is the SDA pin, which is pin number 21, which is GP16, and the SCL pin is GP17, which is for SCL for I2C 0. Everything the same, no difference at all. The only thing that's changed from the earlier wiring to this one is swapping the VCC to ground to reflect the pin configuration on here, nothing else, right? And once that is done, programming this is the same, no difference, just that you need to use the SH1106 I2C class. Let me just do that right away. As usual, if you have not copied the file, you can go to this particular website, which is github.com/roberthh. So this is the site, right? You go to github.com/robert-hh/sh1106, driver for sh1106 display. Click on sh1106.py. Once you click on this link, you can see this file being listed here. Select raw. And once you've done this, I did the same thing again. Okay, repetitive. So I'll just say Control-A, Control-C to copy this code. And you can go to the Thonny editor and you can paste it. Looks like it's already being pasted, right? So you can see that the same class or same file, source file, provides classes for both the SPI interface and also the I2C interface. You can use them, right? So you can see there's a SH1106 I2C interface right here. This is what we are going to use. So we need to connect this Raspberry Pi Pico. So I'll make the connection. And click on the stop reset button. So you can see that MicroPython shell is shown up here. Now, in order to test the display, you might want to try the one with SH1106 I2C test, which I will open and show you. Okay, I don't have it here, so no problem. I can just type it off. It's exactly similar to the SSD1306, then some certain subtle parameters in here. But I think I already have a file on my local computer. I'm just going to open that, which just saves time. It's all the same, as you can see. From machine, import pin I2C, and from SH1106 import SH1106 underscore I2C. That's a class we are going to use. And I'm creating a variable called I2C underscore OLED is equal to I2C of I2C controller 0. That's the first interface. That's what GP16 and GP17 is configured as. And we know that SCL is connected to GP17. SDA to GP16, which is the pin 22 and pin 21 of your Raspberry Pi Pico, and the frequency I've set it to 20 megahertz as usual. These are exactly similar to the earlier program I showed you with the SSD1306. It's got almost the same configuration, right? They're all sacred I2C interface, exactly the same configuration. The only thing I do is that instead of instantiating a class which is an SSD 1306 underscore I2C, I instantiate SH1106 underscore I2C. That's the only difference. The width is set, height is set, and I2C is equal to this parameter. Only thing that changes the class name, in my opinion, in this case, right? I'm just going to call display.poweron. There's this particular class. When you instantiate it, you get an object which I'm going to assign to display. I call display.poweron, and now I say display.text of string and the coordinates, the top and the left coordinates. So I'm going to run this program, and I'm going to show you how it works. I'm going to hit on the run button. Oh, there is a error here. It says SH1106. No such priority. I think I'm running on my local computer. I have to save this on this board, right? I didn't do that. So I need to save as Raspberry Pi Pico. Okay, I think there's no SH1106.py also. I need to copy that. So I'm going to save this as SH1106 underscore I2C underscore test.py. And then I have to save this file too onto the Raspberry Pi Pico. If you get this error, import error, no module name so and so, that means the module is not located on the board, right? That's why you get this error. But the file is already open somewhere else in Thonny, no problem. Sometimes you get this error because I had opened this in another MicroPython instance and didn't close it, right? So I'm going to copy this again, close this, create a new file, save it across, and save as Raspberry Pi Pico. Under Raspberry Pi Pico, I'm going to save it as SH1106.py. I think those windows are not shown in this, but it's a process the same, right? So save it. Now it is saved. Now we can actually try testing this file, this program. Let's try to run this. Well, seems like it didn't work. So, okay, you know what's the problem with this? I said display.poweron, display.text. I forgot display.show, right? I need to call display.show. So that's why it's not showing on the screen. So let me just type it off here. I can put it on the MicroPython shell. When I run this code, all the variables I created, these are all available in the MicroPython shell right here. If all goes well, see, the displays object is there. So I can now say display.show and verify it worked. You can see it's a little bit off. It's in reverse. You might need to rotate it. I can see that it printed the string, right? And as usual, you can, let me zoom this a little more and move this below. Yeah. And you can call display dot fill of 0, and you can type display dot show one more time to clear the screen of any content, right? You can do that. So this works. So, and you can power off the display. You can see the interface for both of these drivers or both of these libraries are almost similar. You have the method called .text, .poweron, display.poweron, display.text, display.fill of 0, display.show. All these methods look identical. Both the SSD1306 and SH1106 have a very, very identical interface, almost similar. The only thing that changes is based on how they are connected. If you're going to be using I2C connection, you might need to instantiate an I2C object and pass the parameters accordingly. If you're using an SPI based interface, which is most likely a 7-pin or an 8-pin display, then you need to configure them accordingly. And that's the difference, right? So this video gives you the full range of various OLED displays based on the SH1106 or SSD1306, and how do you connect them with the Raspberry Pi, and how to just test them with a simple program. In the further videos, which I'll be covering connecting sensors and displaying contents from the sensors. I will also show you how you can change the fonts on the display. The default fonts are very small, but there are extra libraries available where you can change the fonts to make it a little blockier, a little bigger, and all that, right? So you can actually configure them accordingly. There are also various other displays of different dimensions available in the market, which I've not tried, but I believe that most of them will fall into either of these chip categories, right? So a little bit of trial and error and you'll know it. But if you're buying it from the market, just find out what kind of display it is from their technical specifications. That might help you save time in figuring out what library you need to use. I hope you found this video useful. It's a long video. I'm sure it's a lengthy video. If you stayed along so long, thank you very much for staying so long. I hope you found this video useful. If you do find it useful, maybe you can subscribe to me, or you can also type in comments if you have any questions or queries related to any concepts I've covered in here. Please do tune in for future videos I'll be making on the same line. Thank you very much. So hope to meet you in the next one.